So now that we've talked about molecular orbital theory, where these sigma bonds are coming from, why the electron withdrawing group is leading, let's get into the more technical considerations of the Diels-Alder. We've mentioned the HOMO with respect to the diene and the LUMO with respect to the dienophile. But why? Well, we explained that the overlap is favorable in terms of sigma bond formation and secondary overlap to form what's called the endo product. So to stabilize the HOMO, again, these are high energy electrons, what we're trying to do is donate electron density into the highest occupied pi molecular orbital. So typically, electron donating groups are added to the diene to stabilize it. The LUMO is even higher energy and needs stabilization from electron withdrawing groups. So the idea is we need to enrich the diene with electrons and maintain the dienophile electron poor. The electron poor dienophile works very well with an electron-rich diene. Now these electron withdrawing groups can be added to carbon 6 or 5 of what's the dienophile. And we said that it's favorable for them to lead. As this dienophile leads from under and attacks the diene from below, the electron withdrawing groups that are leading in this kind of configuration are forced to flip down. Anything that is trans to a group that is leading, for example this group, is forced to flip up. It's called exo. Groups that are pointing towards the inside, for example we see that in cyclopentadiene, where this highlighted carbon here is what's joining the diene together. If you react that with some dienophile, this group flips up, and we've seen that. It forms kind of like a roof shape. And we can see that here. We can form a roof right here. So, that means groups that are pointing in flip up on wedges, and groups that are pointing out are forced to flip down. This whole idea is stereospecificity. The stereochemistry of our two components is maintained in the final Diels-Alder adduct, the final product. So if we have one group leading and one group trailing, they will end up trans to one another. And we see that in example 1. This ester portion, which is electron withdrawing, is leading, so thus it forms the endo. But this methyl ester is trans to that. So of course in the Diels-Alder adduct, it will be trans. This is exo. So this chart is a perfect summary of all the stereospecificity of this Diels-Alder reaction. It is very stereospecific. Now moreover, it is stereoselective. We talked about the favorability of the endo product because that is associated with being formed most readily. The kinetic product may not be the most stable, but what is for certain is that it forms very readily because of the stability of the transition state. And it turns out because the electron withdrawing groups lead, the transition state is actually aromatic, and its stability confers the formation of the kinetic product very quickly. Now the thermodynamic product can form over time, and that's only possible if we regenerate these two individual pieces and then they re-react to form the thermodynamic product. So again, this reaction is reversible. Now with those considerations, let's dive into the one that may be the most convoluted, the regioselectivity of the Diels-Alder. Now example 2 had this aspect of regiochemistry. We're putting the sulfhydryl group here, which is electron donating, at the carbon 2 position. And we have the electron withdrawing group on the dienophile, let's say on carbon 6. Now why isn't the aldehyde being formed right here? In other words, why aren't we getting the 1,3 product? If we call this carbon 1, this 2, and this 3, why isn't the aldehyde being formed here? And instead, why is it being formed here, directly opposite of the electron donating group? Well, it's this aspect of regiochemistry. Now before we get into this, we need to establish that the Diels-Alder product is not ionic. What we're doing here is using resonance as an oversimplification, kind of like a rationale to explain what we're calling 1,2 addition and what we'll see as 1,4 addition, as we saw in example 2 above. So let's try 1,2 addition. This electron donating group is bound to carbon 1. And we'll use the diene here as kind of the manipulated variable. We'll keep this alpha-beta unsaturated aldehyde constant. So we won't manipulate this, but we will change the positioning of this electron donating group. We're saying that the positioning of the electron donating group on the diene is going to influence the regiochemistry of the Diels-Alder. So let's try to analyze this by resonance. We understand that the sulfhydryl group is an example of an electron donator. So what it will do is donate electrons to form a partial pi bond character between carbon 1 and the sulfur in this case. Because of arrow pushing, we can imagine that a negative charge is accumulating on carbon 4 because of this electron donation originating from a group bound to carbon 1. So that's where this delta minus is coming from. The electron donation is causing an excess electron buildup on carbon 4. Now if we look at our alpha-beta unsaturated aldehyde, this goes back to the enolates unit. We understand that the carbonyl is electron withdrawing, and the adjacent pi bond can donate electrons by resonance. So simply the beta position in alpha-beta unsaturated aldehydes has a partial positive moiety, and that's explained by resonance. So using this rationale, we can line up the negative and positive charges together. So what happens then is what we've seen before. Carbon 4 will attack 5, 6 will go after 1 because of arrow pushing, and we establish the 2,3 pi bond, which is seen here in cyclohexene. Now importantly, the electron donating group and electron withdrawing group are directly adjacent to one another. In other words, on this ring, they are ortho. They are only separated by one carbon. So this is what we call the 1,2 addition, because they're directly adjacent to one another. You can imagine this is 1 and this is 2. Now this happens if we have the sulfhydryl bound to carbon 1. Let's try to manipulate that now. If we move it to carbon 4, we get the same outcome. So let's try to move it to 2 or 3. In this case, 2. So here we've moved the sulfhydryl to carbon 2. And as an electron donator, it donates electrons to form a partial pi bond character. By arrow pushing, we can accumulate excess electron density by resonance on carbon 1. That's where this partial negative is coming from. Now the analysis of the alpha-beta unsaturated aldehyde is the same. The carbonyl extracts electrons, and the pi bond here donates to compensate. So the beta position is electron poor. It is partial positive. But the orientation is different, right? If we look at the orientation here, beta is pointing down. So if we use this idea of resonance to explain regiochemistry, we need to bring the charges close to one another. So that is why we're doing a flip right here. We've flipped the dienophile 180 degrees on a horizontal axis, bringing the charge close to this charge. You can think that the negative is attracted to the positive, so we want to bring them as close together as possible. Again, we're not changing the fact that the electron withdrawing group as a part of the dienophile leads. That isn't changing. We've only flipped this across the horizontal axis. So this carbonyl will still lead. It will still form favorable molecular orbital interactions, what we called in the previous video secondary interaction. That's why we get the endo product. Because the electron withdrawing group is now bound to carbon 2, we're getting the para addition, 1,4 addition. Imagining this is carbon 1, 2, 3, and this is 4. They're totally opposite from one another. So you can see how we can use resonance to explain how charges link up, and how the positioning of the electron donator will drastically influence which product you get in terms of regiochemistry, 1,2 addition versus 1,4 addition. Amines, sulfhydryl, alcohols or ethers, even amides are all very good electron donators. Esters, alkyl groups, and even phenyl groups are less so, but these are all groups classified as electron donators, rather by resonance if they have lone pairs, or by the inductive effect if the electron donation is happening by some other means, for example, hyperconjugation. We need to realize, though, that if I put an ethyl group here the same outcome would occur. We would get pair addition. If I replaced the sulfhydryl here on carbon 1 with a propyl group, the same outcome would occur in a very distinct kind of ratio, maybe 90% to 10% of the 1,2 versus a 1,4. So even though I'm using sulfhydryl here, any one of these electron donators will to a greater or lesser extent influence the regiochemistry. Now, as a part of the dienophile, we've been using carbonyls, but there are a lot stronger electron withdrawing groups, such as the nitro group, NO2, even a sulfate. Nitriles are very common. If we put the most electronegative atom, fluorine, directly adjacent to the pi bond, it will extract electron density by the inductive effect. It would do the withdrawal by other means than resonance. These groups are all extracting electron density by resonance. So typically, resonance has a stronger effect on electron donation or withdrawal compared to groups that are withdrawing by the inductive effect. And it turns out aldehydes or ketones right here are only mildly electron withdrawing, the strongest ones being the nitro and nitrile.